What is Class AB amplifier? For the introduction, the Class B amplifier is an amplifier that combines both Class A and Class B. This is to achieve an amplifier with more efficiency than Class A and lower distortion than Class B. This is achieved by biasing both transistors so they could conduct when the signal is close to zero. For the basic circuit, the AB class amplifier consists of two transistors type NPN and PNP, two diodes in forward bias, and two resistors with the same value. The waveform generated is when transistor 1 is on, transistor 2 is off. The condition is vice versa every cycle. The waveform is generated as shown. The crossover distortion can be cancelled out by using diode. For the amplifier comparison, we choose three types of amplifier, that is Class A, Class B, and Class AB. We compare through the conduction angle. For the Class A is 360 degree, for the Class B is 180 degree, and for the AB is 180 to 360 degree. For the overall efficiency, for the Class A is poor 25 to 30%, for the B is better 70 to 80%, and for the AB better than A but less than B 50 to 70%. The signal distortion for the Class A is none if correctly biased, for the Class B at the x-axis crossover point, and for the AB is only for a small amount.
Okay, let's start with the calculation. We want the power output is 18 watt. So we use VIMS 20, RL 5 ohm, and VCC 30. So first, we need to find VL, which is square root 2 times by VI RMS. So we'll get 2.28.28. Then we calculate P out AC, which is VL peak square over 2 RL. So we will get 80 watt. Then we want to calculate P in DC. First, we should calculate IL peak, which is VL peak over RL. Then we will get 5.656 ampere. Then we calculate IDC, which is 2 times IL peaks over pi, and we will get 3.6. Then we calculate P in DC, which is VCC times IDC. Then we will got 108 watts. Next, we calculate efficiency percentage, which is P out AC divided by P in DC times 100%. Then we will get 74.07%, which is suitable, not more than 78%. Power dissipated by output transistor, which is P2Q, equal to P in DC minus P out AC, we'll get 28 watt. So each output transistor, we just divide 28 with 2, then we will get 40 watt for each transistor. For the AC side, we calculate VCC over RL. Then we will get here 6 ohm. So that's all for AC analysis. So let's go through DC analysis. As we know, our BJT transistor NPN, the value of beta we will use 100. The value VB at the BJT is 1.025 volt and IB 26.11 milliampere. Oh, I forgot to put ampere. So first we should calculate ICQ, which is beta times IB, then we'll get 2.611 ampere. Then we calculate IE, which is beta plus 1 equal multiplied by IB, then we'll get 2.637 A. Then we calculate VE, which is from VBE equal to VB minus VE, and we exchange the place VE, and we will get to 0.325 volt. Next, we calculate VBC, which is, this is the formula. We will get 28.75 volt. Next, we calculate VCE, which is equal VC minus VE, then we will get 29.675 volt. Next, we calculate BJT transistor at NPN, which is beta, same. The value at VB is 1.141 volt. The IB is 14.31 milliampere. The calculation is same like NPN. We calculate ICQ, then we get 1.431 ampere. IE, which is 1.44531 ampere. Then we calculate VE, but this is PNP, so VEB equal to VE minus VB. Then we exchange VE, then we will get 1.841 volt. Then next we calculate VCB, which is we will get 8.859 volt. Last one VEC, which is VEE minus VC, then we will get negative 8.159 volt. So that's all about the calculation. Thank you.
Okay, I will show you a circuit of a push-pull class AB amplifier. This is the circuit diagram that I have already drawn. From here we can see the capacitor here, and here is 1000 microfarad. For R1 and R2 we use 9.767 ohm, and for RL we use 5 ohm. For the VCC, positive VCC and negative VCC, we use 30 volt, and for VPeak we use 28.28 volt. So over here we put two diodes in forward bias. In class B amplifier, crossover distortion happen because the transistor needs 0.7 volt to turn on. With these two diodes we can avoid crossover distortion. Then we have these two transistors, which is NPN type and PNP type. So when one of the transistor is turned off, the other one will turn on. So I put input voltage probe here and output voltage probe here. So let's see the simulation. As you can see, the green one over here is the input and the red one is output. Let me change it first so we can see it clearer. Okay, from here we can see the waveform of V out is slightly different from the V in. This is because the crossover distortion is removed from the waveform and get this beautiful waveform. When distortion happen, it can occur to over this one, to this side and this side. So as you can see, the distortion is removed from this and get this beautiful sine wave. It is called class AB because it behave like class A waveform in a sense that V out waveform always follow V in waveform, and it have advantage of B class, which that the transistor do not conduct when there is no V in and conduct when V in is in present. Therefore, the efficiency of class AB amplifier is between 50% and 75%. And that's all from me.
As for conclusion, we have seen that Class AB amplifier contrasts with Class A and Class B amplifier because they do not have a special operating point. The operating point position along this zone will decide both the angle of conduction and the efficiency of the amplifier. If the operating point of Class AB is situated closer to the operating point of Class A, the amplifier would have an angle of conduction in the 270 degree to 360 degree range, thereby conducting more than 3/4 of the signal. We decided to use Class AB amplifier as the output stage combines the advantages of Class A amplifier and Class B to produce a better amplifier design. In addition, Class AB has the moderate distortion. The solution to the crossover distortion is to provide some forward bias for the base emitter junctions. Class AB does not have as much as efficiency as Class B, but better than Class A, as Class A wastes more power and it is the most frequent use in high-power audio work. That's all from me, Khairuni Saizati. Thank you.